Hi there, my name is Christopher Neugebauer. You can find me on the internet as ChrisJRN, and this is my talk about decorators. Now, unlike the talks that I gave at Python conferences in 2019 and in 2020, those were trying to investigate pointed questions about the future and philosophy of Python, but accidentally being all about decorators instead. This year, I'm going to start by discussing decorators and seeing where I end up. In particular, I'm not too interested in discussing ethics or religion or philosophy. Now, what I will tell you is this talk is going to start relatively basic and not end up in that place. Also, we're going to cover a lot of ground, which means I'm going to skip a lot of irrelevant details. Obviously, if you think I've skipped a detail that you thought was important, well, it wasn't. A bit about me. These days, my day job is as an engineer at Toolchain. We're the sponsors of the open source Pants developer workflow system, which makes it easier to run your favorite Python tools more effectively and more efficiently. Internally in Pants, we use decorators a lot, and I'm going to get to that at the end of this talk. But first, a really quick recap of what a decorator actually is. So, say you have a function which does something obvious. When you call it, it does the thing that you wrote in the code. Now, decorators, these are these statements beginning with an @ symbol before the definition statement. These are Python's way of providing a structured way to do something with functions or methods, or in later versions of Python, classes. Now, adding this surprise decorator, it makes our function print a new thing before it executes. Surprise! And this is how that decorator works. Our decorator takes that function as a parameter, creates a new wrapper function, and it leaves that wrapper function in the place of the function that we wrote. To be more clear, when we put a decorator statement before the function, once Python defines the function, it passes the code to our decorator, which does stuff, and then it leaves that new function in the place of the original function. So in summary, a decorator is a function that takes a function and leaves a function. Except that it's not that at all. And to show you why, let's return to our original decorator. Now, under the hood, our modern Python decorated function, that's this bit at the top here, is doing the same thing as our more ancient Python decorated function, and that's the bit at the bottom. What's going on here is that bit after the @ symbol is actually an expression that when evaluated gives a decorator function. That decorator function is itself called, which gives the function that we tried to decorate. So if you wanted to add a parameter to the decorator, you could do it like this. And you end up with functions which are nested 3 deep, which is a lot more confusing than even those 2 deep functions that we saw earlier. You make a function that takes those parameters that we want to use in the decorator statement, which returns a decorator function. The decorator function accepts the function that's going to be decorated, and it returns the wrapper function. And then the wrapper function, well, that calls the function that we defined underneath the decorator in the first place. It's confusing, but it's easy enough to remember as long as you remember how the Python code with a decorator translates that more manually explicitly written Python code. It almost makes sense. And what that means is that a decorator is an expression that is a function which itself takes a function and returns a function. But that's also not correct. Because a decorator, it literally just assigns the result of the decorator function to the name of the function that's passed in. There is no requirement that that value be a function. In fact, there's no requirement that that be anything at all. And that just seems really confusing for things that should just be modifying functions, but at least it explains that a decorator is an expression whose value is a function, which takes a function and does something with it. And that's why decorators are hard to define and quite hard to wrap your head around at first. On the other hand, decorators are weirdly flexible and they unlock a lot of unexpected and useful design patterns in Python that aren't really accessible in any other ways. And they all come from the observation that Python doesn't say what a decorator has to do with that function or that class that you choose to decorate. And so that's what today's talk is going to be about. That there giant pile of question marks. So, for the rest of today's talk, we are going to look at why Python got decorators in the first place, and what decorators enabled in popular libraries and frameworks. And then we're going to finish with some design patterns that decorators make possible. Enjoy. So, first up, we're going to look at how Python ended up with a feature that is, on the face of it, more complex than it needs to be. Now, Python has always been an object-oriented language, but on the other hand, a lot of people who worked on Python early on had come from languages like C, and C is very much not object-oriented. And what those C developers liked about Python is that it was possible for multiple developers working on different files to be able to name their variables and their functions the same thing, and not have to worry about consumers accidentally using the wrong function. And the Python feature that enables this is called namespaces, and namespaces, as Tim Peters put it, were one honking great idea which Python should do more of. And the way that we did namespaces in the first place was with modules, file structure in Python, but it turns out that's not actually enough. Say you have a class that pairs a name and an address. Now, Python gives you the ability to create one constructor, and so you make the fields the parameters, but in practice, you might want to create an object from a serialized form like a JSON dictionary, or since it was the 1990s, I don't know, an XML file or an INI file or something, whatever serialized form you want. Now, to do this, you would need to use something called a factory function. A factory function is a function that lives in the module but next to the class that you want to instantiate. And it does the jobs here of taking the serialized form and making those parameters and passing those to the constructor. Now, these aren't great. You can't namespace things intuitively except by module name. It's only the name of the function that makes it clear what we're going to get from the factory function. And just like C, we need to use long, redundant, non-clashing names to make sure that we have uniqueness. Because if we have more than one class in the same module, we need to make sure that the names of the corresponding factory functions don't clash. And this is a code organization nightmare, and it's exactly why namespaces are a honking great idea. And so this being the late 1990s, early 2000s, Python looked to the world's source of inspiration on code organization, which was Java. Java has very firm ideas about how code should be organized. And one thing that Python would never allow was multiple constructors on a class. But there's one thing that Python could borrow, which is that Java has this idea of a static method, which is a method that gets called on the class itself rather than on an instance of the class. It has this as a first-class language feature, and one thing it allows is to organize factory methods underneath the class where they logically belong. This would be something that would be really nice to have in Python. So when Python 2.2 was released, it added a fancy new feature. You could define a method inside a class, and then after you defined it, you could say that this method is a class method. And then when you wanted to call that method, you'd call it on the class and not on an instance of the class. Class method and static method were two ways that Python decided to do more namespacing. Now, this idea of naming something as a class method without using a new language feature to do it was called the decorate pattern. And with the decorate pattern, people were happy that they could namespace their code. Now, this decorate pattern, by the way, is something that I'm going to come back to quite a lot in today's talk. We're going to call it define, consume, throw away. And define, consume, throw away is an anti-pattern in most other languages, but it's something that we reluctantly accept in Python. Now, I got sidetracked. As I was saying, very, very quickly, Pythonistas discovered a problem with this decorate pattern, which is that if you have a really long method, a really long method that is so long that it goes off the end of your screen, then it becomes really difficult to notice that the method that you defined is being decorated as a class method. And this is a case where it became really quite difficult to read Python code and understand what it was doing at a glance. And so, very quickly, they decided to do something about it. PEP 318, which had a very catchy name, Decorators for Functions and Methods, came up with some goals for inventing a new language to make the decoration thing much easier to approach. And it's actually quite a fascinating read. It covers a lot of the thinking around Python at the time, like this here, the idea that there might be a JIT compiler in Python at some point. But most importantly, it noticed that decoration was hidden and it should be moved to the front of the function where it's more in your face. And decorators, as it turned out, turned into a really interesting feature in Python. It turned class method into something that was easy to use rather than something that was awkward. And it started making other ideas in Python a lot more accessible. So a second idea of object-oriented programming is encapsulation, or the idea that a class has ultimate responsibility for its data. Now in Java land, the way to ensure that data is controlled is to make sure the data fields themselves are private, and then you gate their access using a method. And then if you need to change an implementation detail, you just change the method and the calling sites are taken care of. And there's no real difference between a stored property, like filling here, you just return a value, and a synthetic property, which is one where you have to calculate that value first, like is chocolate here. Now, because Python never really had private fields, it never discouraged people from directly accessing fields in objects. So by convention, it meant a visible difference between a stored property and the synthetic property. One you have to call like a function, the other you don't. And it made it hard for library authors to change from a stored property to a synthetic property. So Python invented a decorator called property, which came around at the same time as class method and static method, but people didn't use it because it was awkward. Now with property, you can start with a class that has some stored properties and some getter methods, and by replacing the getter method with an at property, it actually lets you access the synthetic and the stored properties in the same way, by attribute access, and it lets you refactor from a stored to a synthetic property without breaking compatibility. Now you don't need to call awkward setter and getter methods, nor do you need to know if a property is stored or synthetic. Even though it changes the semantics of these methods that we've defined, it's actually clearer to the calling context what you need to do to use the class. So the decorator syntax meant that properties caught on immediately in Python, and plenty of languages have stolen it ever since. And properties are an interesting case because unlike the decorators we started off showing, there doesn't need to be any wrapping going on behind the scenes. In Python's case, property works by adding some magic inside the internals of classes by intercepting an attribute lookup. The decorator just needs to do enough to tell subsequent calls to getAttribute that this is a property. And really, this here is all you need to do. Python's implementation is a lot more complex, but the seeds are there. Add some interception code to getAttribute, add a decorator to leave information for getAttribute, and our new decorator has the same basic effect as Python's property getters. Decorators and Python's model where you can access the internals of a lot of parts of the language mean that you can really alter the semantics of the language to make your libraries easier, more powerful to use. And that's meant that decorators have been used in a lot of interesting places throughout the Python ecosystem. For example, the functools module in the standard library is full of decorators that you might find interesting. But I think it's particularly worth calling out Django, because it realized that decorators are a really useful way to apply frequently reused code to functions. Now Django, it uses decorators as behavior modifiers for views. For example, require HTTP methods tells Django which HTTP methods are acceptable for a given view, which saves you from having to remember to write boilerplate code during the function to say what method it accepts. And Django uses decorators all over the place. It's made the great observation that sometimes there are structured, repetitive behaviors that fit into the pre-call and the post-call parts of a function that are much better suited to wrapping than they are to using mix-ins or other object-oriented behavior. So we've seen why decorators happened and what things they brought into the world of Python. We've seen post-processing, we've seen techniques for code reuse, and we've seen ways to selectively add improved semantics without needing to add new language features. But these aren't the only things that decorators let you do. I want to show you how decorators open up ways to solve programs that other languages have solved with features like anonymous blocks. Some of these things I've thought about and talked about in the past, some of them are new. I am not convinced that any of these are good ideas though. Only these are things that are cool. You might want to try them out, you might not. The first feature I want to talk about is the idea of a scoped block. This is something I talked about in my 2019 talk on anonymous blocks. I didn't have a good Python solution for it at the time. One of the things that blocks help out is with maintaining variable scope. So any given block of code doesn't depend on variables that are defined on an inner block. And my thinking on this came from my time working in Kotlin, which has this philosophy that everything is an expression. So if you have a web framework that needs to take a user response or an error response, you only need to assign to this response variable once. If it's a user, then response is assigned the user response. If it's an error, it's assigned the error response. And this looks reasonable in Python if you don't have to deal with error handling. But when you start to handle the error, well, you have to define this response variable inside two different inner blocks and then handle it in the outer block. It's not very nice, it's easy to make mistakes, and there's a whole pile of Python tools that just don't like this pattern of code. You can refactor it by pulling that if statement out as a function, and our original function now has the same structure as the one that doesn't have error handling, but you need to divert your gaze to a different function to see the inner behavior, which is bad visual locality. It also gives you a new visible function that you may need to support, even though you only intended it as a one-off. The alternative is to put the throwaway function inline in the original function, which is better for visual locality. You don't even need to pass a parameter in anymore. But what's more annoying is this define, consume, throwaway behavior. You're writing this function so you can call it once and keep the result, and that's not clear at a glance until you read the entire body of the function. Sometimes this code is going to get called, but it's not clear when. We can solve this with a decorator. And here's that decorator. It's called run. And all it does is it calls the function we're decorating and returns its result. In practice, you define a function that takes no parameters and returns something that you want to be stored in a variable. You put the run decorator before the function, and then you magically end up with a variable instead of a function. And this is useful for that branching block that we were looking at earlier, because we can go from using define, consume, throw away to defining our variable by using the run decorator. This gives us the advantage of scoping our variables correctly. If we had any in this function, we define them at the level where they'll be used. We get the scoping benefits of a single-use function, but without the poor visual locality of define, consume, throw away, which is really cool. The next cool thing I want to look at is this idea of stream transformations, which Python is actually quite strong at already. Except if you want one of the transformations you want to make to apply, to need multiple lines of code to write effectively. Python has for the longest time avoided having multi-line lambdas, and this pattern is one that lets you take advantage of those multi-line lambdas. A stream transformation is something along the lines of a list comprehension or a generator expression. List comprehensions, generator expressions make a lot of sense when you only call a single method on your input iterable, or if you can string from one transformation to another with minimal branching. But if you want to do something that requires quite a bit of branching, well, that's when things get awkward. This is a variation of that define, consume, throw away anti-pattern, which we know by now is just not very good to use, especially since other languages, including Kotlin, Swift, some others, have begun to figure out this problem. If you have a lambda expression as the last argument inside the parentheses, you can pull that out of the parentheses. And then combined with their if expressions example in Kotlin, you end up with an implementation that's really quite elegant. Now, we can't really get this list comprehension here into a nicer syntax in Python, but we may be able to do something with Python's legacy map function instead. So previously, we would define a multi-line function, and then we would call map using that multi-line function, multi-line parameter function as a function, which is define, consume, and throw away again. Let's use a decorator to get that map call up the front where it's more in your face, so it's clear we're defining a parameter to map. We're going to define a decorator called apply, which takes a transform function like map or filter and an iterable, and then accepts a real function as the thing that does the transform on each element. And you use it like this. You apply map to the items using the function we're about to define, and you store it to the output variable. And with that, we can take our define, consume, throw away code and turn it into something where we say what we're going to do with the code before we define it, in exactly the way that we would with a single line lambda expression. So That's a couple of patterns where you can use decorators to avoid define, consume, throw away, an anti-pattern. The next thing I want to talk about is the builder pattern, which is actually well established in the Python community, but the way Python uses it is ugly. We like writing our data structures in Python in code, but there's only support for a small number of officially blessed data types, dicts, lists, sets, strings. Builders are a way to create data structures in a way that isn't restricted to what the language provides. But in its usual form, there's a lot of repetition, and there's this side problem of defining the thing, but not showing how it's going to be consumed until much later. And indeed, the first things you define here are often the very last things you consume. This is not so much an issue in this here reasonably flat data structure, but as things get more nested, the lack of visual locality becomes really difficult. But generally speaking, builders are almost always used like this. You create a builder, you do the things that add to the data structure, and then you build that data structure. So we can do that to build up a data structure like an HTML document, for example. This here HTML node builder class takes a tag name when we create it, has a build method that puts everything together, but what's interesting is this node method. This node method is actually a decorator that creates the builder, passes it to the function that we're going to be decorating, and then it builds once that function returns. We can create one more decorator to string it all together, and suddenly you end up with a function that defines an HTML document, but actually has that nesting structure and that visual structure of the document that we're creating. It strips out all those repetitive calls to create a builder and to build the builder, and it just leaves us with the task of building up the data structure. Now, unlike our previous pattern, this one encourages you to write more functions, but in doing so, you end up with code where you interact with much less boilerplate. Now, the final pattern I want to show is one I call the Code Registry. Unlike the previous ideas, which are really geared towards structuring single-use functions in a nicer way, this one is about separating your idea of how you define your code from how you call it. And the example I want to show is an idea for a library for handling text processing pipelines. Say that you want to figure out the most frequent word in the Zen of Python. Well, you can do that with Unix pipelines, and with your Unix pipeline, you'll definitely get a result. Now, to do this task in Unix, you need to know all of the different Unix commands. You need to know what does what thing and what order to call them, tokenizing the words, stripping punctuation, normalizing into lowercase, etc., etc., etc. And doing this in Python really isn't much better. Indeed, the code is a lot more explicit, but you need to know a lot more things. What would be cool is if I could ask Python to give me a result of a particular type with a set of characteristics, say a list of pairs of instant strings, which are made up of lowercase words with no punctuation, which represents word frequency in ascending order. So we have an idea. How do we turn that into a reality? Well, the idea at the center of this is a code registry, which in our case is a class with a decorator that associates a function we're decorating with an input scheme and an output scheme. In this case, the decorator just returns the function that we decorated. We don't need to wrap it in anything, but we do store it for safekeeping inside the code registry with some attributes rather than the name that we gave it. And with the registry, we can define small functions that represent all the steps in transforming our data. We say that we have a function that accepts an iterable of strings with some attributes and returns a counter of strings that represents those same attributes as well as the frequency attribute. And you can define as many rules as you like that handle various text processing functions. And once you've done that, well, you can make a function called findSteps, which figures out how to get from an input type with attributes to produce an output type with attributes. And with that, you can write a function that does the steps and the processing that you want. And if you've ever written code in Prolog, this is basically the same thing. Now, this idea of separating the act of calling your code from the place where you define it is really powerful and actually shows up in a lot of places. In Flask, the app router is a registry that you populate with decorators. The route decorators that you use specify the circumstances in which a responder function will get called. And it's closest to home for me in how it's used in Pants, which uses a rule registry to figure out how to get from a set of source artifacts to a shippable artifact. So a developer tool workflow can be defined as a series of small steps, and the engine will figure out which ones to call. More importantly, third-party developers can provide their own rules, which helps Pants figure out how to deal with different sorts of artifacts. Pants will figure out how to run those rules automatically. And this is a really nice way to handle extensions or plugins. And finally, I wanted to point out that even though this approach separates the idea of the name of a function to how it gets called, this decorator still returns the original function unaltered, which means you can call it to directly unit test it. So that is the end of our whirlwind tour. We've seen what decorators have allowed in Python, and we've looked at 4 design patterns that show some unexplored ideas that are enabled by decorators. The first is the idea of throwaway functions. While they're not truly anonymous blocks in the way that other languages offer them, decorators are definitely the closest thing that we have. And a lot of the patterns that other languages use with anonymous blocks can be approached with decorators. We also saw the idea that decorators are great for transforming functions into the data they produce, which is useful for programmatically building up data structures. And we saw how the complicated builder pattern is replaced by something a lot more reasonable and readable. And we saw that code registries allow decorators to allow you to associate functions with a purpose rather than a name, which means you can call code based on the data you have rather than on the name of the function. And that is it. Thank you so much for coming along. If you have any questions, you can email me at the address that's on your screen. There's also a Twitter handle there somewhere. If you're after code snippets, I'm going to share them on my website at chrisjrn.com. Finally, thanks to all the organizers who made PyGotham happen. It's been such a pleasure to share this talk to you, and I'm looking forward to seeing you at another one of these events in the real future. Thanks for coming along. I really appreciate it. Bye.